I'm Julian. I'm a developer advocate at AWS working with the serverless team, and I love helping developers turbocharge how they build applications using all the cool things Lambda can do. Rajesh.
Yeah, hello everyone. I'm Rajesh Pandey, principal engineer with AWS Lambda. I've been with Lambda for 6 years now, and in that time I have watched Lambda grow from thousands of customers to like millions of customers, and it's been an incredible journey for me. And I'm looking forward to sharing some of those fun stories with you all today.
Cool, excellent, can't wait. Yeah. So today we're going to continue actually a series of different Lambda under the hoods over previous reInvents to help you understand Lambda a little bit more. And I'm going to go over some Lambda fundamentals, how various invokes work, and spend some more time on our polling capabilities. And then Rajesh is going to come back in and head proper down the rabbit hole and do some interesting lessons on how we built Lambda, how we made the choices we did, and even more information on the pollers. Now, to be honest with you, a part of the magic of Lambda is a lot of what we're going to cover today you don't actually need to know. We just handle it all for you. It's a super amazing service, and we love explaining how it works, so it doesn't seem so mysterious, just maybe magical in how it works at such great scale. So let's start with a trivia. Who wants to know probably the biggest secret of servers? Anyone? Well, actually, there are quite a lot of servers underneath, sorry to tell you. Hundreds of thousands, in fact, and you as a consumer never see them. Because we, AWS, manage all of this underlying infrastructure for you, allowing you to focus on your business scenarios. And with Lambda, we like to think of that you just bring your egg, your code, the life of your business, and we've built an incredibly resilient nest at scale to look after your egg. Because it means you don't have to build a whole bunch of things yourself. Things like auto-scaling logic, AZ failover, retry logic, connection pooling, backpressure, lease management, all these different kind of things. We take that on so you don't have to. And this obviously runs at massive scale. More than 15 trillion invokes each month, with a whopping 1.7 trillion invokes just on Prime Day alone. 99.99% availability and resilience built into the service so you don't have to pay extra for it. And so let's do a recap of some Lambda fundamentals. One of the major technology foundations of Lambda is the open source Firecracker, but now we're actually expanding the foundation to include good old EC2. Lambda Managed Instances, announced on Sunday, gives you Lambda's operational simplicity with EC2's range of instances. You can choose to use Graviton, or CPU, or memory, or network optimized instances for your Lambda functions. And you don't have to manage any of these instances for you. You also get up to 12% savings, 12 times savings for at-scale workloads, and multi-concurrency and EC2 pricing incentives, all part of the package. There's also a session, CNS423, which you can find out more about it. With normal Lambda, so-called on-demand, everything runs in the Lambda service VPC, and invokes come in from clients and ultimately run on EC2 worker hosts owned by Lambda in the Lambda service VPC. With Lambda managed instances, the control plane stays in the Lambda account, but we provision and manage EC2 instances in your account, in your VPC, and then route function invokes to containers running on them. So Lambda on-demand with Firecracker and Lambda managed instances, two different compute models, but the rest of the architecture basically stays the same. Lambda's got 3 invoke types: synchronous, when the caller calls either directly or via API gateway, and this sends the request to the Lambda service, does its processing, waits for a response before returning it to the client. When you do an async request, either via client call or maybe something like an S3 change notification or an EventBridge rule matching, sending an event, you don't wait for a response from the function code, you hand the event off to Lambda, and Lambda just handles the rest. Places the event in an internal queue, and it returns a successful response to the caller saying, I got your event, and then a separate process goes and processes it. An event source mapping is a Lambda resource that reads items from a queue like Kinesis Dynamo, or from a stream like Kinesis and Dynamo, or from a queue like SQS, and a producer application would have put messages onto this, and then Lambda manages the pollers, which we're going to cover today, to read the messages and then send them onto your invoke for processing. The Lambda API is the front end where all requests to the Lambda service land, and it is multi-AZ, a load balancer resolving to lambda.whatever region name .amazon.aws.com. And then this routes the invoke request to the data plane and then ultimately lands up on a worker host, yours or ours. That's it. That's the journey of events in Lambda. Rajesh, I think we're done. Okay, there's obviously a little bit more which we can talk to you about today, so we should continue. The front-end load balancer distinguishes control plane requests from invoke requests, and these can be function configuration or resource management from the console, CLI tools, or an SDK. The data plane requests the route, then routes it to the separate data plane, one for sync invokes and one for async invokes. And the sync invoke service is actually technically called the front-end invoke service, and async the event invoke front-end service. But, naming things gets a little bit confusing, so we're just going to stick with sync and async to keep things a little simpler. And this is actually a deliberate choice to separate the data planes, which was built into the system a few years ago when basically we had a huge async spike which overwhelmed the sync service, and so now we can protect the sync service from async floods. The data planes are also a fleet of stateless hosts. Lambda, again, is an AZ service, a multi-AZ service, so you don't have to worry about load balancing your functions across multiple AZs. Lambda handles it for you. For performance and stability, the data plane needs to get information about functions from the function versions Dynamo table, which we cache both on the hosts and also in an L2 AZ cache. Because we want to make invokes as fast as possible, so we want to avoid having to look up things on every single invoke, and it also helps with availability, this way of doing it too. So let's now look at the synchronous path in more detail. So the ALB distributes the invoke request to a fleet of hosts as part of the sync invoke service. I'm simplifying the diagram here as it's going to get a little crazy, but Lambda is built so everything runs across multiple AZs. So the sync invoke service first performs some authentication and some authorization of the request, and this is going to ensure that Lambda is secure, as only authorized callers are going to be able to even get through Lambda's front door. The service then is going to load the metadata with their request. The front end also calls what's called a counting service. This is going to check whether any quota limits may need to be enforced based on the account or reserved concurrency. The counting service is also optimized for high throughput, needs to be under 1.5 millisecond latency as it's called on each invoke. And as it's critical to the invoke path, it's also highly available across multiple AZs and super fast. The front end then talks to what is called the assignment service, and also there's a control plane service, another component which manages then the coordination and manages background tasks. It handles those control plane things like creating functions, and then also manages the lifecycle of assignment service nodes. Back to the assignment service, so this is going to then coordinate the placement service. And so for the first invoke of a function, a new execution environment needs to be started on a worker host. The placement service is then going to create an execution environment on a worker with a time-based lease. It's also going to monitor worker health and make the call when to mark a worker as unhealthy. So once the execution environment is then up and running, you can see the init path. The assignment service is then going to give your supplied IAM role, and also environment variables with the IAM roles with the privileges you define, and then also the environment variables, and give it to the worker. The execution environment is then going to start the language runtime, whatever it is, Node, Java, Python, and then download the function code or run the container image. And then the function init process runs. Then the sync invoke service runs the invoke, and your function runs and sends the results back to the caller. To minimize latency, it's called directly to an invoke proxy on the worker hosts. And then when subsequent requests come in, well, the front end's going to talk to the assignment service, which says, yes, we have already got an execution environment all up and running, and he's going to route the invoke payload directly to that execution environment, and again, run the handler. When the lease of the execution environment is up, or there's some kind of error, the assignment service is able to gradually drain the connections, spin down the execution environment, stopping future invokes. So let's take a little bit of a deeper look at some of the Lambda workers. So a worker host is just a standard bare metal EC2 instance in which we place execution environments. Now, to be efficient and get invokes happening as fast as possible, we actually maintain empty micro VM pools on the hosts in various different memory sizes. When an invoke comes in, the host management can then allocate the smallest memory size to satisfy the request, and then download the code or image. And this then speeds up things a lot, as it can be a bit of time to get an execution environment up and running, and so we do them in advance. For Firecracker workers, Firecracker is the process that sits above the OS and then manages the single secure execution environment for invokes. Within the execution environment, we maintain some of what we call sandboxes. And these are basically privileged container namespaces, one for your function code, the runtime and extensions, or your container image. And then we also maintain a separate managed sandbox, which your code can't access, but allows us to manage the things inside that execution environment. And an interesting thing is we've actually completely re-architected how this works this year to improve Lambda for how it works today, and also to build even future functionality. And it's been rolling out across our fleet, and you actually wouldn't know it unless you knew where to look. Trillions of invocations happening, and we're basically swapping the tires of Lambda while the car is moving at crazy speeds. Outside of the sandboxes, we also run a management agent for control plane functionality, and also then a telemetry agent, which allows us to get metrics and logs out of the execution environment transparently. The worker host then has a bunch of other components. Host management coordinates with other services, builds and destroys those execution environments. The invoke proxy is the direct link from front end to your code. We also need to store micro VM files like runtime binaries on the host for faster loading. And then we maintain a cache for container images and as many things as we can for performance. We also have agents that then need to talk externally to the container image chunk plane. This is for downloading container images, and S3 for zip archives to get your function code into the execution environment. And of course, this needs to connect elsewhere, and so there's networking to connect to the outside world. For Lambda managed instances, it's actually pretty much the same, although we're not using Firecracker, but containerd for the logical separation, and then containers instead of actually micro VM execution environments. So let's have a look onto async. So it works in a similar way to the sync service, but only handling async event requests. And we've also recently increased the payload to 1 megabyte, so you can now use it for even more use cases. The front end then sends the invoke request to an internal SQS queue and responds with an acknowledgement with the caller to say that Lambda is going to invoke your function asynchronously. We got your request. Lambda is going to manage the SQS queues, and you don't actually even have visibility of them. We run a number of queues and then dynamically scale them up and down depending on the load and the function concurrency. Some of the queues are shared, but we also send some events to dedicated queues to ensure that Lambda can handle a huge amount of async invokes with as little latency as possible. We then have a fleet of Polar instances, which we manage. We're going to cover that in more detail. And these Polars read the messages from the internal SQS queue and then determine the function account and the payload. And then ultimately, it's going to send the invoke request synchronously again to the sync invoke service. As you can see, all Lambda invokes ultimately land up as a sync invoke. And the function uses the same sync pathway I talked about before, returns the function response to the Polar, which then deletes the message from the queue. If the request is not successful, the Polar then doesn't actually delete the message from the queue and uses the same visibility timeout as you would with your own SQS queues, and then the same or another Polar can pick up the message and try again. You can also configure event destinations for async invokes to provide callbacks after the processing, whether the invokes are successful or they're failed or after all the retries are exhausted. Some other control plane services are involved. There's the queue manager, which needs to look after the queues. It's going to monitor them for any backups and does the creation and deletion of the new queues. And then it works nicely with the leasing service, which then manages which Polars are processing which queues. And it can also detect when a Polar fails, and so that their work can also be passed to another Polar. So let's look at now the event source mapping or the Polar invokes. A producer application is going to then put messages onto the stream or queue asynchronously. We then run a number of slightly different Polars as we have different clients depending on what the event source is. And this is a very similar architecture to async invokes from then on. The Polars read the message from the stream or queue, can also filter them, batch them up, and then send them up to a single payload. And it sends to your function synchronously with the same sync front-end service. Remember, all Lambda invokes eventually land up being synchronous. Then for queues, the Polar can then delete the message from the queue when your function successfully processes them. Depending on the event source, you can then send information again by the invoke to SQS, SNS, EventBridge, S3, or even Kafka for Kafka sources, which we announced recently. There are also a number of control plane services, again, state manager, stream tracker, depending on the event source, manage the Polars, manage the event sources, discovers work, and then handles scaling the Polar fleets. The leasing service is going to assign Polars to work on a specific event or streaming source. If there's a problem again, it's going to then move its work to another Polar. And there are also architectural differences between two types of event sources, queues and streams. So queues is for individual task processing when each message is independent and messages are deleted after the processing. And streams is then for when you're doing, when you have multiple consumers, maybe need the same kind of data, and order particularly matters. And then messages are going to be retried for replay. Two different architectural styles. And the Lambda ESM provides a bunch of functionality across all of these event sources. We've got filtering, batch controls, including for streams, being able to split a batch to find a faulty record. We've got choosing where to start in a stream, retry and failure handling, analytics for Kinesis, and some platform performance configuration options. And the cool thing is, the Lambda ESM handles this all for you. You don't need to think about the different characteristics. Beyond just configuring your ESM, we take on the task of making everything actually happen. So let's look a little deeper at the ESM and see how it works with both streaming and queuing. The ESM polls the event source, the queue or stream for available records. Now, so we need to think about even getting actually to the event source. SQS and Kinesis are on public endpoints, but we also have event sources that are connected to private subnets or even outside AWS, often with Kafka. So we need to handle that as well as the actual functions which could be connected to a VPC. Authentication depends on the event source. AWS ones, we can use IAM, but for Kafka, we want to support all the possible options, authorization methods, so the ESM can actually authenticate. If there's ordering, things like SQS FIFO or streaming sources, we always need to ensure that the ordering is maintained with the message processing. For streams, you can configure the starting position as part of the ESM config from the beginning, from a particular timestamp, or just getting from the latest records. And the ESM also then needs to remember where it was in the stream using the offset or sequence number. We need to handle retries, or resharding. Streams can grow or shrink, and so we need to continually look at the source and see if there is maybe a new Kafka broker online or new shards or partitions to process from one of the event sources. The parent shard is split, creating a new child shard, and we need to maintain ordering during this process so we can send the right records to new Lambda functions to then scale up the processing. For Kinesis, there's a helpful additional setting called tumbling windows, which you can use for data aggregation. You can pass a state across multiple separate Lambda invokes to aggregate data in real time, sort of quick and easy alternative way for some analytics solutions. There are also two ways to consume from Kinesis. You've got a shared fan out where you have to have up to 5 consumers can share and read throughput of a stream, and then each shard supports a read rate and a data rate, and this has got a latency of about 200 milliseconds. But for faster responses to stream data, you can actually set up Kinesis Enhanced Fan Out, or EFO. This actually changes the flow from the ESM pulling from Kinesis to Kinesis sending to the ESM using an HTTP push mechanism to get to the data to the ESM faster, as low as 70 milliseconds. So the ESM figures this out, manages the change in logic flow, and this is just handled transparently, something you don't have to look after yourself. There's also a dedicated polar offering for SQS and for Kafka and recently actually SQS, where we can also provision event polars in advance to be able to handle spikes. You can configure various settings, mainly the minimum and maximum polars, to be able to control the throughput. And this can dramatically increase your polling scaling and throughput. 16 times for SQS, up to 20,000 concurrency compared to the standard polling of 1250 for SQS. Kafka also simplifies the networking and the cost models when you enable this, and there is an additional charge to be able to do this, and it's based on an event processing unit, which you can manage. And so provision mode is great for high traffic sources where you want low latency, and also this can save you some polling money at big scale. And provision mode allows us to build and bring new functionality to the polars, like supporting schema registries and allowing efficient binary formats like Avro and Protobuf. Okay, so we have done the polling, then the filtering allows you to dump records you don't want to process. Why? Well, filtering is a CPU-intensive process, and you don't really want to do that and waste Lambda invokes in your code. So you can have positive filtering to include messages that you do want to include, or negative to exclude all messages that don't match a particular specific criteria. This is very flexible using the same syntax as EventBridge filtering. And here in this example, we are processing messages for the tire pressure less than 32 to send only those to your function. Next up is batching. Batching actually the records for grouping the records for efficient processing. And this means you can control your Lambda invokes for efficiency. So how are batches defined? Well, you get to configure this and control this in a number of 3 ways. You can configure the size, and this is 1 up to a default of 10,000. We normally start at 10, the number of items in the batch. But yeah, up to 10,000, that is really big. And then the batch window is to help improve efficiency when you don't actually have much traffic, so you can at least process messages before a whole batch is formed. And you need to also stay within the Lambda 6 meg payload limit. So once there is a batch, we then need to invoke the function via the sync control plane. So we need to then consider different scaling for the different architectures. Streaming is actually an upper bound problem. You want to process data with a stream generally as fast as possible. And so there's a maximum throughput you want to factor in. So with Kinesis and Kafka streams, you're trying to consume and process messages at the highest rate possible to keep up with the incoming data and to minimize the lag. And the challenge is then scaling up to exceed or meet at least or possibly exceed the ingestion rate. But Queuing is different. This is actually a lower bound problem. You do want to process data efficiently, but you also want to ensure you're not actually overwhelming downstream services like APIs or databases. So with SQS, the queue is actually acting as a buffer or a shock absorber, and you are then controlling the rate where you want to drain the queue to then protect those downstream resources. And the challenge is then maintaining a minimum safe processing rate that is going to respect those downstream resources. So two different architectural styles. And so for SQS to do this, we want to manage the flow control, the rate at which Lambda consumes the messages. And so you can configure the max concurrency on the ESM to control how many concurrent executions the ESM is then going to attempt to send to Lambda to prevent overwhelming the downstream services. And this is actually the all-important buffering control. Reserve concurrency is then a separate setting on the Lambda function, which you set to reserve capacity from the function, and this ensures it can scale up if needed within the available account concurrency. So you actually rather want to use the max concurrency to manage the buffer and the flow, but you can also use both together, and if you do, you want to make sure that the reserve concurrency is higher than the maximum concurrency to prevent any throttling. So for also streams, we need to scale up how the stream scales. This is automatically, the ESM just needs to figure this out. Kinesis scales by adding shards and Kafka by adding partitions, and Lambda is automatically going to figure this all out and is going to scale up the consumer polars to match the incoming throughput. Still with message ordering in each partition or shard. More shards or partitions means more processing. But customers wanted even more processing for Kinesis, so we came up with what's called parallelization factor. By default, it's one function per individual shard, but you can scale up to 10 for massive Lambda throughput, still maintaining the order. And this is something built specifically for Lambda for high throughput stream processing. For error handling, streams and queues also have different semantics. Streams need to produce or preserve the ordering, but you actually need to figure out and decide what to do with the poison pill message. Should that actually stop processing? If it's something like log data or bank transactions, absolutely, you want to stop the stream processing and you want to fix the problem before continuing processing. But maybe for some frequent sensor data or GPS data from a hire car, you can handle some of that data loss because in a few seconds' time the next result's going to come in and you can still continue shortly. So in this scenario, you don't actually want to stop the stream because you want to keep the message processing going. And then for queues, generally you don't want to stop for a failed message and you want to continue to process the rest. And we then have two batch error handling things to give you some more control. Partial batch response is when you know the failed record and you can turn a successful response, and then tell the ESM which message has failed, and then that's going to go to be retried and processing continue. And AWS Power Tools for AWS Lambda is a great utility for using for lots of languages, and that's got a batch processing utility to help with this. And for streams, bisecting batches can be super useful when you don't handle the error, and it's not something you normally need to consider for queues. So in this example, message 3 is a bad one, although we wouldn't actually know it yet, and so we process the batch and get a failed response. Instead of endlessly retrying the same batch, the ESM can then split the batch, try the first half to keep ordering, and try to get more messages processed. The split batch fails again, as it has the faulty message, and so the ESM splits again, and we now try and process the new batches. This time, the first batch processes successfully, and the single batch with the poison message fails again. And we can then continue with the original second half of the first batch to keep up that ordering of the successful messages. And then can fully process as many messages as possible without having to reject a whole batch and then deal with a faulty message if we want to. Really efficient way that you can control. And then we need to handle function errors, so we need to configure Lambda on failure destinations for the function invoke issues. And then you might think, well, why are there actually two different error handling paths for SQS? Well, the SQS deal queue is going to capture messages that fail repeatedly during the polling or the processing, while the on-failure destinations is going to capture invoke errors with your Lambda function, and this could be things like network issues or throttling, or maybe you've deleted the function or there's a function permission issue. And so both serve different processes and can be used together for comprehensive error handling. And so that takes us through the Lambda fundamentals. We've covered sync, async, workers, polars, and all the features of the event source mapping. Again, it just looks like a configuration option, but Lambda underneath the hood is doing a huge amount of work, doing some polling, doing some pushing, doing some pulling, being as efficient as possible to be able to get the messages from the different architectures of your streams and your queues. So let me now hand back over to Rajesh, who's going to dive deeper into the polars and talk about some of the lessons we learned about when we were building Lambda.
Okay. Hello. Thanks, Julian. Yeah, the cold start. Yeah, Lambda with a cold start, you know. Hi, hello everyone. Again, this is Rajesh. Today, I'll be talking about, let me give you the overview of I have divided this segment of the talk into two parts. One is I'll walk you through the mental model of some of the mental models that we have used while designing Lambda and the operational complexity that comes with it, and how that complexity actually fueled a lot of innovation that we have baked into Lambda design. So let's start with the mental model first. Last time, we stood here and convinced you that Lambda in some ways is a storage service and applies a lot of learnings from building services like EBS, foundation service like EBS. And this year, I want to convince you that Lambda is also a queuing service, and how we have applied a lot of learnings from building queuing services and the queuing theory concepts. I know compute as a queuing service seems a bit counterintuitive, but let me explain what I actually mean by that, and I'll walk you through the thought process of designing this Lambda service. So what's a queue service? Let's start with that. I started with Amazon back in 2013, so it's been more than a decade. And the first thing that I did was build a queue processor. And basically, a queue processor there's a message buffer where a lot of events and messages are stored. And there is a worker which actually polls. So you write a way to deal with the queue, and then you have a business logic that you process your messages and do something with it. And for that, I had to build a lot of simulations. And I had to build a lot of simulations to go through, model my upstreams, model my downstreams, what are the failure points, and what would it take to build a resilient service. Back then, Lambda didn't exist. So I had to do a lot of heavy lifting, and I had to build the queue processor from scratch on my own. And when I joined Lambda, that is 2018-19 time, I realized that the same pattern shows up everywhere. Many of the features that we built and many of the things Julian just walked you through are inspired by that same analysis. I've been doing this since 2013, as I told you, over a decade. So let me quickly walk you through the queuing theory. So that will set the foundation for the rest of this session. Queuing theory is nothing fancy, but just basically study of the waiting lines, how things arrive and wait and get processed and leave. This diagram is basic. This is a basic shape of every queuing system you have probably you see. Probably you have seen some version of it. Events arrive at some rate, and that rate is never defined. Some customers go crazy, they spike. Some are slow and has bounded arrival pattern. On the right side, what you see is a worker. Their speed is the service rate. Just like arrivals, this isn't constant. Sometimes your dependency can take more than, if it is taking 10 milliseconds, sometimes it can take 100 milliseconds. So this is also not well defined. So you have to model different things around it. And next, what you see here is the buffer, burst, and variability. The variance is when you are building a queuing service, there comes a lot of variance in terms of if there's a spike or if there's a thread issue or if your service is not able to hand up, deal with the process, deal with the workload, then it may run into some issues. And that variance, a simple one variance into the system can lead to build up of the backlog. So I'll talk more about it when we go into specific sections of this. So let's look at the lessons that Lambda has learned from the queuing theory and how it applied it. The first things I want to talk about is the lesson that we learned from queuing theory is buffers smooth variance. Arrivals are never uniform. They are busty, they spike, they are unpredictable. And so we don't try to handle them right away. That's impossible and expensive. You can always provision for the peak, but then you would end up paying a lot more for it. The second lesson is we specialize workers for workload types, and I'll talk about how this led to design of how Lambda in terms of how we separated pollers from the Lambda execution environment, and why the nature of different the poller worker is different than the execution environment. And the third is the control variance to prevent instability. even if an average arrival rate is less than average service rate, variance can cause temporary instability, and that variance kills the system. And the fourth is like coordinate shared resources through centralized control. In queuing theory models, the work conservation means if there is a work and if there is a server, so server should never sit idle, basically. But theory assumes there is always exists a global state. In distributed system, you have to build it. And I'll talk about like how Lambda has to build it. So let's first start with like this buffers smooth variance. As I was talking about, like the traffic pattern is always variable. There are customers with steady state traffic. There are customers with random traffic. Some customers spike, extremely spike, like they can spike from like 10x to like 50x. And you have to have a system which actually takes care of this thing. There are some customers, those who are like slowly ramping up, and suddenly they become the whale customers. And some of the customers can burst, like can have micro bursty patterns. That you have to have a system which can actually handle this. And like, so what you're basically building is an ingestion tier, where there are data sources, there's an ingestion tier, and there's a storage layer, where the system, the traits of that system is that it can accept highly variable multi-tenant traffic. You need to, after you've taken the traffic, you need to normalize and validate the request. And you have to write the message or events to the right queue. You have to persist it and acknowledge it. Before acknowledging, you need to make sure that like it's persisted durably. And then you also have to apply admission control and backpressure to protect yourself. So if you have to build something of this sort, you would need to, you need to have a durable architecture which actually helps you build this like ingestion tier. So what Lambda did, this is like the layer of the customers, they're variable customers. What we do, we have a load balancer where like whenever the first time that you invoke, so like Julian was talking about like front end and invoke and event invoke front end. So this is the front end that is the event invoke front end. And it has a bunch of things like the distributed load, like health checks and all. And once you have that, like it hits the other front end, like this is called like a reverse proxy, you can call it that, which is like multi-AG service and has like bunch of like hosts in it. And at the same time, it also has a like auto-scaling rules, so that like if there is a spike in heat in CPU or memory or a bunch of these things, then it can auto-scale on its own. Apart from that, we also have to build, like once you have gotten the ingestion tier done, like you also have to persist the message, as I was talking about. So you have to have a buffer. And this buffer needs to be durable in the sense that like you can't lose message once you have told it to your customers that like we have accepted a message. But also at the end of the day, the thing that you want to do is like it should go into the queue where you can process it. We don't want to just ingest the message, but we also want to process it. So how do we build that like routing layer in between? Let me walk you through that. So first thing is like there's an invoke request that comes in with the event message. Then it goes through a chain of validators. You do authentication, then you do validate the payload, then you look at the function, whether there's an active function or not. And then once you pass this validation layer, you need to find the queue where that message can be ingested. And again, like I was talking about, we have millions of customers. We can't have like millions of queues. So there has to be like some sort of like a multi-tenancy within the queues. So for that, the most popular pattern I think you guys might have seen is like building a set of queues and then hashing them onto like an hash string, and then doing that multi-tenancy for the customers. So what we do when a message passes through all the validation chair, we find the queue finder, we hash it onto like the partition of the hash string, and once we have found the partition, we take that message, we have gotten the queue, and then we write it to that queue, whatever that queue that we found on the hash string. But this is, as you know, like even the single partition can get like really, really hot, because now millions of customers, a lot of them can overlap onto like the same partition. So what we do is we went back and then we use a technique called shuffle sharding, where shuffle sharding is nothing. Basically, it's like instead of like hashing a customer onto like a single queue, now you can hash that customers onto like multiple queues. So what we do is we hash a single customer based on the account ID, and there are like some heuristics that we have. We hash that customers into like now 2 hash ranges. We pick the queues based on those hash ranges, and then find the queue which has the lowest queue depth at that time, and then insert the message in there. So this is what we do. This is what we call like shuffle charting, and it does wonders for us. And it helps us remove this like hot partitioning, and it goes away. In addition to this, we also have something called like express lane. So once we know, like, okay, we know this customer is going to be noisy and it will be having a lot more traffic, we already create like a sideline queue for them. We let them like absorb, and we absorb their traffic. And then once they're done, we can reap their queue and back them into like those dynamic shared queues. And this was what I talked about so far is like the queues that are managed by Lambda. Those are like event invoke queues. So whenever you ingest Lambda, invoke Lambda in like asynchronous manner, that is where it goes. There's another part of the buffer, which is like helping us like smoothen the variance, is like customer owned. So this is like the event source mapping side of things, where like the queues and the streams and everything stays on the customer boundaries. All we do is like we have the processing. And from this point onwards, the polling becomes same for both like the, either it is customer managed or it is service managed. So the second lesson that we applied, that specialized workers for workload types. Let's look at how Lambda applies this lesson number 2. To understand it, let's first understand what a worker is. This is not typical worker, but a worker is nothing but a processor which looks at the queue, and whenever it sees a message or an event, it processes it. What queuing theory showed us that heterogeneous servers with different service rates need to be dealt differently for best performance. We applied this, and we separated the polling workloads from execution workloads. Both polling and execution workloads are different in nature. Polling is continuous, stateful, connection heavy. On the other hand, execution is busty, stateless, and short-lived. So what you see here is there are actually 2 types of worker. One is a polling worker that is managed by Lambda, and there is a Lambda function that like customers write. Julian talked about this side of the worker and like the Lambda worker execution environment. I want to dive deep today onto like the polar worker. So let's jump right in. So what are the key components that make up polar? I divided and I looked into like what we do today. So this changes all the time. We learn new things and we evolve. So this is what we have today. What we have like a work acquirer. This component looks at like if there's an active work. So it looks into like an assignment manager store. It says that, okay, there's an SQS cube or there's a stream, there's a work that is there. So what it does, it picks up the work and starts the event source configuration. So like in the case of a stream, like for KCL, Kinesis, it's KCL. For Kafka, it's Kafka consumer. For SQS, it's SDK, SQS client. What it does, like once it is configured, it kickstarts this work, it configures the connector, and pulls the record, and then writes it into like an in-memory queue buffer. So a lot of features that Julian was talked about are being done in this like in-memory queue, where we create this view so we don't kind of pressure the event source. And we build this view, and this is where like you do batching, your filtering, your schema registry validation if it supports that. Then we have this like an invoke orchestrator layer, where once you have your batch is ready, then batching can be for different ways of batching. Julian talked about like 3 of the ways we do the batching. Once you have the batch ready with your conditions defined, you do the invoke orchestrator. What it does, it like invokes your Lambda in synchronous manner with the batch, and it deals with the record. If it is failing, then it hands it off to like the error handling component, which writes to DLQ or retries whatever is appropriate based on your configuration. In addition to this, like if your message is successful, we have a checkpointer manager which actually deals with like an advancing the checkpoint. So that like this says that, okay, before deleting a message, we make sure that like your system has processed it and we are not losing any message. In addition to this, this is an autoscaler we have. So it looks at the current state of the system and says that, okay, whether I need to autoscale. If I'm running hot, I should look into the signals of my worker right now and say that, okay, I need to scale further. And scaling can be in two parts. One is like vertical scaling. If I have a capacity in my host, so I look at the footprint of my memory and CPU and say that, okay, I can vertically scale to absorb some more traffic. Or if I cannot, then I will signal it to like some of my global coordinator to say that, okay, I need more help. So can you like spin up new workers for me and then like take on that work. Apart from that, if I'm running hot, I also want to load shed some of the workers. So like we have a load shedding component which actually removes the work if I'm running hot. I don't want to impact my customers. In addition to that, there's like an overall like health checker which keeps looking into like different parts of the system and making that data available to different components. So autoscaler looks into that data and says that, okay, oh, I think I'm running hot, I need to autoscale. And load shedder said, okay, I'm running hot, I need to load shed something. In-memory queue buffers also, like similarly, like it builds that view and then makes it available to like different components. So what we did so far is like workers and the view of that worker and like what it takes to build that worker. But not every worker is same. Some workers are more secure. Some need to like go through the VPC boundaries. So what we did is like we went back to the drawing board and looked hard at it, that what is the anatomy of the polars and what can be done there. So if you remember, this is what we just saw, and we squinted, like literally we squinted and saw that like, okay, if we slice the worker horizontally, we basically get the bottom up part where all the system touch points are. We squinted even harder, and I'm talking literally, I squinted a little harder. A bottom half can be further divided into 3 parts with 3 different touch points. And let me share what I meant by that. If you look closely, the one part of that worker is actually dealing with the event sources, and one part of the worker is actually dealing with the internal service communication, doing the internal service communication, and another part is dealing with like the Lambda private invocations. And all 3 have different security boundaries that you are operating with. So what we did is we said, okay, let's pick this part of the worker and wrap it into like one specific set of security boundary, then pick this set of the worker and put it into one specific security boundary. And the last part was like Lambda execution environment, which like you can have a private VPC function that we can invoke. And what else? Like we applied the same principle that we applied to Lambda worker and Lambda polars. We applied the same principle within the Lambda polar workers and said that, okay, even there are 3 parts. So now we can automatically scale a part of that worker, which is independent and has nothing to do with the rest of the worker. So think about like if you have worked with Kafka, then you know the problem around consumers rebalancing. There's a like death loop, and there are a bunch of things that has been done, like the static stability, static membership, and then cooperative rebalance. What if we can separate these 2 things in such a way that like you can deal with the consumers separately, then actually increasing throughput by invoking Lambda functions? So we did that. We wrapped them into security boundary where like one is like dealing with the customer resource, one is dealing with the internal services, and one is dealing with the function execution. So we can have a VPC peering between execution environment and the polar workers. We can have a cross-account connectivity with the customer event source, and then internal service where like this is within the same boundaries where it is operating. Now that we understand polar workers, let's look at the next lesson that we got from the queuing theory, which tells us about the production behavior of these workers. Let's look at that. The lesson number 3 is the control variance to prevent instability. And as I said, like variance kills systems. So let's take a deeper look at it. What you see here is a workload which has a high latency. Once it has gone through and like now started to absorb a lot more resources of the system. And that leaves like the workload B and workload C with no resources to work with. And as Little law dictates that if processing latency increases, concurrency will spike even with a constant arrival rate. Now at this point, we want to build some sort of like a fairness in our system. So what do? To deal with, we built multiple layers of defense control, different layers of like mechanisms to maintain the stability into the system. The first one is like variance reduction. The first layer is if you're getting messages into the queue, try to batch them, for example. The second one is like the capacity controls. Set hard limits, like capping the concurrency. So a single function can't overrun the fleet. Third is control what comes in. Throttle requests when you're full, just like a store locking the door at the capacity, for example. And backpressure, react when overloaded. You don't have to suffer. Slow down, polling, or shed low priority. These are like 4 layers that we have built. Again, these are layers that we have built, and some of these layers can be configured by the customers. And some of these are like owned by and managed by service team. Now that we have looked at the arrival pattern, workers, and what keep these servers running, look, one more thing that I talked about is coordinate shared resources through centralized component. What queuing theory says that, okay, there is always a deterministic or stable pattern. Whenever one worker dies, the other worker picks it up. We don't have that luxury in a distributed system. So like we have to build this global state on our own. What it takes to build that global state? So global state has 4 traits in it. One is work conserving scheduling. Is like if there is a work and if there's an idle worker, we should try to pair them up. Conflict-free assignment. If one worker is working on it, don't give it to someone else so that they're not like thrashing each other. The capability of your dispatch, like you are giving work to someone and it can handle that specific work. Like I don't want to give like a queuing worker an SQS work to an stream poller, for example. And the failure detection recovery. If someone has claimed the work and it is actually not working on it, then I should have a way to know that someone is not actually actively progressing that. So what do? We have a control plane. Basically, like whenever you create an ESM or you create an event invoke config, it goes to that, it goes to a config store. And then we have an ESM lifecycle manager, whose job is to bring worker and make it available to the system so that it can work on it, act on it. Then we create an assignment. With that assignment, there's another separate service called assignment manager, where it stores the assignment details into the config. And this is where like we build that global state. And as I talked about, like the polar worker, it gets the work, then it heartbeats and sends the metadata back to the assignment config store, which is the source of like we having the global state. And at the same time, like this is like an anti-entropy job, which is making sure that everything, whoever is claiming the work, they have the work and they're acting on it. And if they're not acting on it, then I want to involve the human operator so that like it can take an action on it. And this leads to what you saw, what Julian showed you, the Lambda polar worker architecture looks like. And you have seen it like multiple times. And this was the under the hood part of building this kind of architecture. Let's quickly recap. Ingestion tier and buffer, you need to have a buffer smoothing mechanism. There are worker and there are different types. Some has a different traits, so you should like try to separate them out. The stability controls, variance kills your system, so you need to have like controls so that you can maintain and build stability to your system. And the global state that is needed for you to like make the continuous progress, and this is what we need to keep fleet healthy. And this basically tells you almost everything that you need to know about how Lambda applies lessons from queuing theory. And hope by now I give you some idea on like why I said like Lambda is also a queue service in many ways. And Lambda has millions of customers and trillions of events flowing through these systems. So how do we keep everything running? Seeing everything up front is really, really hard. As a vice person said, it's like everything fails all the time. So once you have the queue, you have the worker, what do you do if it fails? So this second part of the talk I talked about is like how do we deal with the operational complexity on operating a queue service like this? Obviously, we had to innovate on different dimensions to run it quickly. In queuing theory, it tells us that the failures are independent, systems scales linearly, and saturations happen gradually. It's the kind of world you would like to see as an engineer. But the moment you operate a real multi-tenant distributed system, you realize that everything gets messier. The reality is there are correlated failures. If one service fails, you see like, oh, other service starts to fail. System don't scale linearly. If there's a retry loop happening somewhere, then they accelerate faster. And they'll cliff drop. It's like you model something in your simulation, you always miss out that one condition which leads to like some sort of like a cliff drop. And when I say cliff, I mean this cliff. If you remember, back in 2013, Lambda had an outage where a latent bug in our front-end feed surfaced, and that led to increase in error rate. This is the cliff I'm talking about. It's really, really hard to model all the cases while you are testing. Same in the case with the queuing service. You can't model everything. But what you can do is like build a system which can recover from this. While there are many things we do, I captured 3 main resiliency patterns that we can apply, to operate Lambda. The first one is like dependency outages. What do we do when the core dependencies that we rely on to build this queuing service goes away? The scale inversion. What if like a bigger fleet starts to hammer the smaller fleet? What do we do? And the third is like availability zone outage. It's very special and very unique to like the problem, how we solve it, and like how it is different for like operating a queuing service. So let's start with the dependency outage. Let's look at the recent outage, October 2025. I think it's pretty fresh in everyone's memory. This was the recent DDB outage with a bunch of services got impacted, and Lambda was one of them. We used DDB for various things to operate our data plane. The root cause of this issue was a latent race condition in DynamoDB DNS management. I think there is a talk you guys should attend if you're interested in what happened here. Now, if you think from the point of view of a queue service operator, this becomes even more interesting. What you see here is that when an outage happens, we start to accumulate messages. Now, when the dependency is recovered, we have to deal with backlog that we have accumulated with the new traffic which is coming. And to catch up, we have to now start, like we have to work twice as hard, right? We have accumulated some messages, and the new set of messages are still coming in. So what do we do? The second kind of thing that we see is like a fairness conundrum. What I call it is like a noisy customer is a noisy customer, but a good customer becomes noisy customer because now there is no way for us to like, that noisy customer has hundreds of thousands of messages or millions of messages. A good customer, a good citizen also has like millions of messages now because we were out, so we started to accumulate. Like how do we differentiate between that? And so what do we do? Like whenever there is an outage, we want to clear the backlog as soon as possible, but we also don't want to hammer our service down so that like we delay the recovery. It's a balancing act. It always turns into a balancing act for us whenever there's an outage. If we are underflowing, then we are delaying your recovery, so your message is staying in queue longer. But if we are overflowing, then we may tip over the service, which is actually, because there is a capacity that we have provisioned, and there is like a finite amount of work that you could do. You can like have buffer, and you can unlock a lot of capacity, but still there is the amount of work log that you have accumulated can take more time. There are a few things that we do, and I'll talk about like some of those strategies, and this is not exhaustive by any means, but there are a few things which are interesting. I want to share that. One thing that we build is, we build a gradual ramp using a token bucket. That token bucket rate is controlled through the view of the system. So like how our CPU and memory pressure is looking, how is our sync traffic looking, how is our different modes of invocations are looking, and then we build that and tune the rate of our TPS that we are generating through this like asynchronous fleet to gradually recover, so that we are not tipping over, and then we have this handshake mechanism every time there is an outage. We build this automated handshake mechanism where we keep looking into like dialing up the knob and then looking at the rate at which like how our service is recovering. We also try to convert a FIFO queue into a LIFO queue, wherever, like if you have a backlog and you are okay to go ahead and then start looking into the fresh messages, so we start to try to create and shard the customer. So the old message, the backlog can drain slowly, but your new messages, so that's why you see recovery very fast. We also sometimes, if you have a function, you have a version, so we try to shard your queues into like a function and a function version and then an alias, so that you start to see recovery much faster. And then, as I was saying, a good customer can become noisy, a noisy customer is a noisy customer. So like, how do we isolate these things? So for that, like, think about like a customer has like millions of messages and set their function concurrency to 1. So how do we deal with that? Like now that customer is in the queue, we try to isolate that customer into its own queue so it can have its own processing because it's not a noisy customer. It's the outage that made it noisy. So we have another kind of like a token bucket mechanism where we assign a set buffers or like give tokens based on whatever the function concurrency downstream configurations are, and we assign that one single specific token bucket to that customer, and then like try to isolate them so that like they have, even if they are in the shared queue, they are now using that token bucket to say that this is their processing capacity. So this was about like what happens when dependency is out. There's another kind of outage that we have to deal with is like scale inversion, whereas a big fleet is depending on a small fleet, and a small fleet goes out, or a big fleet behaves weirdly, which leads to a small fleet going out. So this is another outage where like a large surge of connection led to and a restream happened, which led to a small fleet going out, and then also at the same time like the control plane was like recovering, which delayed the recovery. And for us, it becomes, if you think about like that work did global state view, like the leasing service is out. If this is out for like 1 minute, we have accumulated messages, and we have keep continuing to getting like new messages. So how do we recover from that? And it becomes that problem for us. And so for that, like we build static scalability. What I mean by static scalability is the ability of a workload to continue to continue operation despite dependency impairment without requiring reactive changes. The most critical step to achieving this static scalability is separating the hot path from the cold path. Data plane doesn't need to call control plane during the processing. Control plane only needs to like do the lifecycle management, and data plane is sufficient to operate in the steady state. One of the strategies is like we push down the configuration. For Lambda's case, we push the Lambda function configuration down to the pollers instead of like poller asking for that work. The second is like replicating the state, like L1 and L2 cache. I think Julian talked briefly about it. We also use disk as a backup so that like we can consume the work and like restart the work, resume the work where it is, if there's an outage. And then build stickiness with a flexible timeout. So we try to reduce the false positive from like the false negatives. If there's an outage and we see like it's a temporary outage, don't leave your work. Don't release your work. Lease-driven independence means partitions has their own dedicated worker or shards are dedicated workers. And the circuit breaker is like if you see like the error is spread across the whole fleet, that means maybe there is nothing common with like that one specific host, but it is spread across the whole of the system. And the third kind of outage is like availability outage. What I mean with that, like availability outages are very weird. There can be like a thunderstorm somewhere, and that led down to outage of like an availability zone. So what happens for us, if there is an AZ, there are 3 AZs, it's a sample workload. If there's one AZ out, we have to migrate because we have millions of queues that we are processing, and there are millions of workers and their relationship. So like we have to migrate that active workload from that AZ to another AZ. And that migration requires some effort on our side. So what do we do? Like we have AZ buffer. This is very standard. Like if you have processing capacity and you need to move the work, you need to have the buffer so that you can take on the work. The second, and again, this is like another balancing act for us, where like if you are one AZ is impacted, you need to move the work to like the other AZ, but you don't want to impact the other AZ also with it, with that outage. So we have like heartbeat-based mechanism where like we are reactively, like we let the leases expire, and then that becomes available and then gets shared. But it takes longer time. And what if like Lambda has recovered our workers? We have moved the workers from like unhealthy AZ to like healthy AZ. Now we need time to, and if we are taking time to migrate, then there is no point in like having that recovery. So we need to get more proactive in that. We have divided that into like 3 parts. Like detection, we need to first make sure that like there is an AZ outage. We are very confident about it. Then we evacuate, and then we continuously observe that like there is an outage. There is like the work has migrated to that new AZ, and then like when the recovery happened, we need to move it back. So the key takeaways are architectural key takeaways: design for robustity, unpredictable, reduce personability, isolate, and operational key takeaways around multi-tenancy is the default. failures are constant, and stability comes before scale. And with that, I'll hand it over to Julian.
Excellent. Thank you very much. We've only got a little bit of time left, but I just want to quickly go through some of the new things with Lambda. We talked about Lambda managed instances, all the flexibility of Lambda with EC2 control plane as well. Lambda durable functions, the whole way, messes up all the way you're thinking about Lambda. Built for asynchronous processing, but all within a single Lambda function. Build long-running workflows in your favorite programming languages. Another session is happening on that this afternoon. Tenant isolation, providing execution isolation between tenants. You just give a tenant ID. This is great for SaaS customers who have maybe hundreds of thousands of functions. Makes it much better for them. Event source mapping enhancements, we've got schema registry, which has been released, the provision mode for SQS I mentioned, and also a whole bunch of ESM metrics were available to help you building your applications. And the future, well, of course, there's plenty more to do. We'll always be helping with observability, bringing new updates, new runtimes as quickly as we can, working hard on price to make Lambda applicable for all workloads, more deeper integrations with AWS and third-party services, and always we continue to listen to your feedback. Let us know what you would like us to make to build. Our Lambda roadmap is now public, available on GitHub, so you can help us define the future of Lambda. Lots of other kind of sessions, managed instances, durable functions, the future of serverless tomorrow, and I did a talk on best practices yesterday. Hopefully that'll be on YouTube and useful for you as well. Another slide here, just on a bunch of a lot of serverless kind of things to continue your serverless learning. But most importantly, thank you so much for today for coming early in the morning. I appreciate you taking the time to learn a little bit more about Lambda. Hopefully you can understand there's a huge amount that happens under the hood, so you can just consume Lambda as a great service without having to worry about all the flow control, all the other kind of things that Rajesh and his team is building. So thank you very much for joining us today, and enjoy the rest of your re:Invent.